The Space Shuttle Approach and Landing Test Program began in February 1977. The Orbiter Spacecraft Enterprise was mated atop
Let's look to the future, when the shuttle program will have progressed to sending missions into deep space. Within our normal experience on Earth, we don't need the results of general relativity. Its ideas seem remote, an abstraction. But far from the Earth, at speeds and accelerations which are higher and in gravitational fields which are stronger than those on Earth, we will see that the laws of general relativity become quite natural. Such environments do exist. Indeed, they're commonplace. There are many stars which would provide them. This is the control base for mission Einstein, a remotely controlled deep space probe, named for the discoverer of general relativity, who himself liked to clarify his ideas by thought experiments. To him, those experiments were purely imaginary. Today, they are close to reality.
Mission Einstein has been in progress for a few months now. The robot astronauts Ein and Zwei will make routine maintenance checks. Let's activate them.
You've knocked over the boxes.
We should be weightless. Everyone knows that in space you're weightless.
We're in a gravitational field. Look. They hit the ground at the same time, just like Mr. Galileo said they would. A sure sign of gravity.
Zwei, something else is causing it. I can't find anything large on the viewer, just distant stars.
You are in deep space, being propelled at 1G thrust toward the planet Zerkovsky. Please check fuel consumption rate and lock on stellar guidance system. We can easily understand how they confuse their accelerating state with the effects of gravity. When objects are released out in space where no gravity is acting, then they stay at rest. That's just Newton's first law. No force, no acceleration. But there is a force acting on the space probe delivered by its rocket motors. And so the floor of the ship will accelerate toward the objects and hit them both at the same time. Now, the fact that this behavior is also observed when gravity acts on falling bodies is just what you would expect from Galileo. Two objects dropped from the Leaning Tower of Pisa would hit the ground at the same time, if no other forces were acting. But until Einstein came along, this observation about motion under gravity was considered to be a remarkable but an isolated fact. In the language that Newton gives us, it is described by saying that for any object, the inertial mass, which controls the acceleration due to any force, is equal to its gravitational mass, which determines how much gravitational force an object will receive from other bodies. At the end of the 19th century, Baron Roland von Oettwisch established this equality of inertial mass and gravitational mass by experiment to within 1 part in 10 to the 8. Now, this remarkable accuracy impressed Einstein so much that he used this equality as a cornerstone in the construction of the general theory of relativity between 1908 and 1915. But he took it further, and he turned this isolated fact of Newton's into a principle, which he called the principle of equivalence. Not only could the robots be fooled by acceleration into thinking that they were under gravity when they dropped things, Einstein postulated that no experiment that they could do with the equipment they've got on board could serve to distinguish the effects of acceleration from the gravitational effects of some suitably chosen distribution of matter. The effects of gravity mimic the effects of acceleration. Gravity and acceleration are equivalent. But I wonder how things are progressing in the Einstein probe.
The longitudinal communications laser has turned blue. It should be red. It was red when we set out. The ship's specifications say it should be red. We must tell the controller.
Don't waste the controller's time. Lasers emit light of one color and one color only. You should know that the laser was red when we set out. It is red now. Your perceptual apparatus is faulty.
No, it's not. I've switched on the aft laser. It's red also.
Very well. Obviously an effect of acceleration. We must tell the mission controller. Mission controller, our laser beams change color as they travel up the ship. Is the principle of equivalence right? We don't see these effects on Earth.
If you shine light upwards against the pull of gravity, then the same frequency shift should occur. But don't forget, your rockets can produce a much greater acceleration than that due to gravity on the surface of the Earth. So our equivalent frequency shift would be of a much smaller magnitude, and it would be a formidable experimental task to measure it. But it was done. The crucial breakthrough came in 1958 with the discovery that gamma rays emitted by certain radioactive substances in crystals could have a very sharply defined frequency.
This is a gravitational laboratory, old style, an isolated shaft set in the center of the physics building at Harvard. It was brought back into use in 1960 to observe the effect of gravity on the newly discovered precise frequency nuclear gamma rays. The gamma ray sources are prepared as very thin foils. The one for this experiment is, in fact, cobalt-57, which becomes iron-57 when it emits the very special gamma ray of exact, precise frequency. When it's operating, this source would be down here in the temperature-controlled box. And from this, gamma rays spread out in all directions. Some of them go up the tube. The tube is filled with helium rather than air to minimize the interactions of the gamma rays. So the gamma rays can travel unimpeded. The question is, what does gravity do to the gamma rays as they travel upward? At the top of the shaft, 22.5 meters above the source, there's a foil of iron 57. Now, this would absorb the gamma rays very strongly if they're exactly the same frequency as they were when they left the source. But if they've shifted a little in frequency, because the gravity up here is just a little bit less than it is down below, then there'll be a bit less absorption, and that will let more gamma rays be transmitted, and they can be counted in this detector here. So the net effect of a gravitational redshift is an increase in the counting rate here. But the effect's very small. It has to be checked. And one way of checking it is to invert the whole apparatus, to bring up the source from down below and take this detector downstairs. And that has to be done many times, no mean job. And after months of doing that and counting and checking, the final result came out to be very close to general relativistic predictions, within 1%. But even so, it would be nice to do better. It would be nice to have a greater height. But with gamma rays, they're fanning out all the time, and so there's no point in going much higher. You simply run out of gamma rays. Radio waves, on the other hand, can be beamed, and that gives a different way of doing the experiment using much greater heights. The most stable and precise form of radio oscillator is a hydrogen maser, an atomic clock, if you like, using hydrogen. Now, an identical twin of this hydrogen maser has been sent up in a rocket to 15,000 kilometers, and the rate of this clock compared with the rate of a clock down on the Earth. Unfortunately, the rocket's moving all the time, so there's also a Doppler shift. But that can be corrected for very accurately and carefully by using a separate radio link with the ground. And the final result from this experiment is the most accurate test yet of general relativity, and it agrees within a precision of 2 parts in 10,000.
Mission controller, look. When I shine the laser across the cabin, the light is bent. Can you see that in gravity?
The principle of equivalence says that if you observe light bending in an accelerating rocket, then we should observe it in a gravitational field. But again, it's a question of size of effect. On Earth, it's much too small to see. But Einstein used that form of argument to predict the bending of light in a gravitational field. So he looked around for the strongest gravitational field available in which to test it. And that's the field produced by the sun. So in 1911, he predicted that starlight passing close to the sun would be bent enough for it to look as if the star's position was slightly shifted. Now, this prediction was tested 8 years later, in 1919, and a deflection of position was observed, but a deflection of approximately twice the value that you would predict using the principle of equivalence. There's more to light bending than we yet know, but we're in good company. When Einstein first made the prediction, even he didn't know that.
Mission controller, we've stopped in the middle of nowhere. There are no planets here. We are weightless.
You're in orbit around the planet Zerkovsky. Look at the viewer. As the probe orbits, it's really in free fall about the planet. Since gravity accelerates all objects at the same rate, the robot and everything around them accelerate at the same rate. And effectively, they feel no gravitational effects acting on them. They might say that they were in an inertial frame.
Something strange is happening. As I float, the two parts of me are drifting apart.
This time you two have really found something. You're observing the variation of the gravitational field of the planet Tsiolkovsky. And that's why we need an extra ingredient to complete general relativity. You see, the two parts of you are on slightly different orbits that go apart and then come together again. And that's why we have to specify in the principle of equivalence that the effects of acceleration are the same as the effects of gravity for a suitably chosen distribution of matter. You see, if we could design a completely uniform gravitational field, then its effects would be exactly equivalent to those of a uniformly accelerating rocket ship. But the fields of real matter distributions aren't uniform. They vary in strength from point to point. And if that variation can be observed, then it can serve to differentiate gravity from acceleration. However, within a small enough spatial volume, or over a small enough period of time, the effects of the non-uniformity can be made as small as desired. That is, small enough so that it can't be observed with real equipment of a given standard of precision. Ein, can you observe the same effect with your individual components?
Yes, but it takes a long time before I notice anything.
That's the essence of the principle of equivalence as it applies to real gravitational fields. If both the spatial extent of the observing volume and the time of the observation are sufficiently limited, then the effects of the non-uniform gravitational field cannot be observed with any real equipment. And if the observers within this restricted space-time region are in free fall, then they are justified in saying that they are free of any gravitational influence. And with no gravity present, we know that the laws of physics that they will use to explain physical phenomena, such as the behavior of their lasers, will be those laws based on special relativity. So, the principle of equivalence allows us to predict physical processes even in the presence of a large body of matter such as the planet Tsiolkovsky, as long as we restrict ourselves to a small enough region of space-time and pick the right frame of reference. What we haven't learned from Ein and Zwei is how to describe physical laws on the large scale, such as would allow us, for instance, to pick up that extra factor of 2 in the prediction of the bending of starlight. This move from the small to the large will bring to the fore Einstein's next stroke of genius after his exploitation of the principle of equivalence, his conception of space-time as curved.